Hi, I'm Nirav, a PhD student in the Computer Science Department at Carnegie Mellon, and today I'm excited to talk to you about our work on caching with delayed hits. This is joint work with my advisor and collaborators at CMU and Microsoft Research. Caches are at the heart of performance-critical systems, and here they serve a number of important purposes. For example, caches may be deployed to alleviate bandwidth demand to a bottleneck backing store. They might help improve throughput for memory-bound processes. And finally, they could help mitigate read delays for latency-sensitive applications. Today, we'll focus on this third category of caches, which seek to reduce delays. These are latency minimizing caches, and their goal is to reduce the mean latency of all requests served by the cache. Here's a latency minimizing cache we built at CMU, based on Redis, a distributed key value database. Its goal is to minimize latency for a cross data center KV store. When a request comes in, traditional caching literature would assume that there are two possible outcomes: cache hits and misses. In a theoretical example, I'm going to show you what textbooks say will happen when I run this cache in a real request sequence. Let's see if you can catch what's wrong with this example. Here we have our client talking to the remote server via our key value cache. Our backing store contains three objects labeled A, B, and C. Let's assume that our cache is of size 1 and the RTT between the cache and our backing store is 3 milliseconds. We also have the following request sequence, with a new request arriving at the cache every 1 millisecond. When the first request to A arrives at t equals 0, our cache is empty. Consequently, the cache must first fetch this data from the remote server, and the request experiences a cache miss, with a latency of 3 milliseconds. The next set of requests to A can be served directly from the cache, and experience latencies corresponding to that of a cache hit, in this case 0. We can repeat this process for the next set of requests to B, where we'd expect to see a cache miss and 3 subsequent hits. Hopefully some of you found the bug in this example. If not, here it is. We said that it takes 3 milliseconds to resolve a cache miss. So how is it that the requests that arrived just 1 or 2 milliseconds after a miss were served with 0 delay? Clearly something's very wrong. Let's take a look at what actually happens. The first request to A experiences a cache miss, triggering a fetch and incurring a latency cost of 3 milliseconds. We also know that the RTT to the backing store is 3 milliseconds, implying that the object will only arrive in the cache at t equals 3. At t equals 1, the request for A arrives and is queued behind the original miss. At this point, our fetch request is only 2/3 of the way to the backing store. Since the data only arrives in the cache at t equals 3, this request must wait at minimum 2 milliseconds to be served. Similarly, the request for A at t equals 2 suffers a latency of 1 millisecond. These requests that neither suffer a latency of a cache miss nor that of a cache hit are known as delayed hits. At t equals 3, A finally arrives in the cache, and all queued requests, including the one that just arrived, can be resolved. At t equals 4, the request for object B misses in the cache, and we initiate a fetch that will be resolved at t equals 7. Once again, the request for B at t equals 5 and t equals 6 must wait 2 and 1 millisecond respectively to be served. It's only at t equals 7 that the data finally arrives in the cache, and then the request can be served from there. It turns out that our caches are impacted by a phenomenon that's becoming increasingly prevalent in today's systems, called delayed hits. The reason delayed hits are starting to increasingly matter is that the average number of requests that can arrive during a fetch, a parameter that we'll call Z, is starting to go up. Numerically, Z is the ratio between the latency to the backing store and the average inter-request time, or IRT. It turns out that this is proportional to the product of backing store latency and link bandwidth. Thanks to the efforts of this community, we see a clear trend in these quantities. Latencies continue to go down, and bandwidth continues to go up. However, latencies are quickly approaching their speed of light bounds. For instance, the theoretical lower bound on RTT between Pittsburgh and LA is 34 milliseconds, and we're not too far off from here today. Conversely, the link bandwidth continues to grow at unprecedented rates. For instance, we're moving to 100 Gbps and beyond in the network setting, and memory technologies such as HBM promise order of magnitude improvements in bandwidth over DDR. Here's what this means for caches in practice. Consider a CDN point of presence in Pittsburgh with origin servers in different parts of the world. We expect to see different Z values depending on the latency to the origin server. For a 40 Gbps link, these might range from 1,000 to a local server, all the way up to 226,000 for one located in Singapore. However, as the CDN link bandwidth increases without a corresponding decrease in latency, we expect to see a higher number of requests to arrive during a fetch, increasing the number of delayed hits we see in practice. At 200 Gbps, this number could be as high as over a million for a remote store. In this talk, we'll explore this phenomenon in more detail. First, we'll see that delayed hits break our assumption about how to optimize for caching latency. Next, I'll present an offline latency optimal caching strategy, belatedly, that we designed to minimize latency. And we'll also compare it head to head against the hit rate maximization strategy. Finally, I'll describe how we used insights from belatedly to design an online caching algorithm called MAD that makes traditional algorithms aware of delayed hits, yielding significant improvements over these baselines. Let's look at this first point in more detail. Delayed hits break our assumptions about optimizing for cache latency. Specifically, there are two assumptions that I want to discuss. First, that you can calculate average caching latency using the hit rate, and second, that a hit rate optimal cache is also latency optimal. Now, both of these assumptions are true when backing store latencies are uniform and the parameter we defined as Z is 1 or smaller. However, they're not true when Z is larger. Let's recall how our textbooks tell us to compute average latency using the cache hit rate. First, the hit rate is defined as the ratio of the number of hits to the total number of requests served by the cache. Then the average request latency is equal to the hit rate multiplied by the hit latency plus the miss rate, or 1 minus the hit rate multiplied by the miss latency. So does this expression work? This graph depicts the behavior of two simulated models in the network setting. One that accounts for delayed hits, labeled actual and depicted in orange, and one that does not, labeled idealized and depicted in blue. On the y-axis, we have the average request latency, and on the x-axis, we sweep our Z parameter. We find that as Z increases, the latency estimates derived from hit rate quickly diverge from their actual values. At Z equals 10,000, we see that the error exceeds 60%. So we find that delayed hits subvert expectations of traditional caching models and simulators. And also, they make hit rate derived estimates of latency extremely unreliable. So it turns out that you can't rely on average latency computed using the hit rate. Let's look at the second claim. A hit rate optimal cache is also latency optimal. So what does it mean for an algorithm to be offline optimal? Well, if we had access to an oracle, in this case a helpful wizard, who could tell us the future, then our algorithm alpha opt could use that information to produce an optimal solution. Belody's algorithm is one such offline optimal caching strategy, and it provably maximizes hit rate in the absence of delayed hits. We're in the offline setting, so we have access to our helpful wizard who tells us the future, and Belody uses a simple greedy strategy. If the cache is full, it evicts the object that is used farthest in the future. In this example, for a cache of size 2 containing objects A and C, Belody would choose to evict C since it's used after both A and B. Unfortunately, Belody does not account for delayed hits, and this leads it to make latency suboptimal decisions. Here's a toy example demonstrating this. In this case, we have a cache of size 2 and a Z value of 3. A fetch for object C has just completed, and we must decide whether to evict object A or B to accommodate C. Let's say we choose to evict A. The subsequent requests to objects C and B will be hits. However, we see that there's a burst of requests to object A, resulting in a miss and 2 delayed hits. This yields a total latency cost of 6. Instead, if we had chosen to evict B, the request for B at time t plus 1 would have incurred a cache miss, but the subsequent accesses to A would have all been hits, resulting in a latency cost of 3. As you might have guessed, Belody chooses the first option, resulting in a worse overall schedule. So it turns out that a hit rate optimal algorithm isn't latency optimal either. These observations motivate our design of an optimal caching strategy for the delayed hits problem. However, it turns out that computing such a latency optimal cache schedule even with knowledge of the future, can be quite challenging. Once again, we have access to our wizard who tells us the future, and we have this request sequence with just two objects, A and B. The X's here denote empty time slots, that is, no arrivals, and the sequence repeats infinitely. Given a cache of size 1, our task is to find a schedule that minimizes latency. We also consider these three algorithms: always cache the bursty object A, always cache the paste object B, or simply use LRU. Can you guess which of these algorithms will perform the best? I'll give you a few seconds to think. Okay, it turns out that for z equals 1, LRU is provably optimal and yields an average latency of 0.2 milliseconds. For z equals 5, caching the paste object B yields the lowest latency. For z equals 17, our decision changes again, and yet again for z equals 22. So we find that the optimal caching strategy highly depends on the value of z, and even an educated guess, such as always cache the bursty flow, doesn't generally work. We find the answer to the latency minimization problem in the form of a flow network formulation. Our offline algorithm, belatedly, computes empirically tight bounds on the optimal latency and polynomial time. Unfortunately, I don't have time to explain the flow formulation in any kind of detail, but there's 2 points about it that are worth noting. First, it's based on an MCMCF problem, which is the integer version of which is known to be NP-hard. And second, the formulation introduced us to the notion of aggregate delay, which helped us design our practical caching algorithm. I'll discuss this metric in a few slides. So now that we have an optimal algorithm, we're ready to quantify the gap between BELODY, that is the hit rate maximization strategy, and true latency optimality. The next set of graphs depict the percent relative latency difference between BELODY and belatedly. Here we look at three different application scenarios: 10 Gbps network traffic, CDNs, and storage. For each one, we'll consider a range of Z values corresponding to different use cases. In the 10 Gbps network setting, we find that for low latency operations, such as one or more DRAM reads or an RDMA access, the gap is quite small. However, as we move towards WAN latencies in the milliseconds, we see a significant gap, exceeding 30% in this case. While we'd have liked to perform this evaluation at 100 Gbps, unfortunately we're restricted by public availability of traces at that line rate. Similarly, in the CDN setting, we see a gap of 5 to 17%. And in the storage setting, a gap of 13% for cross data center latencies. Overall, we see that for scenarios corresponding to high Z values, the hit rate maximization strategy is far from minimizing latency. So the big question is, can we build delayed hits aware caches that provide lower latencies than today's systems? All of the theory that I've presented so far tells us that there's a problem with modeling caches as having only hits and misses, while ignoring the contribution of delayed hits. While this is well and good, what can I do for my key value cache to achieve better latency? After all, in the real world, I don't have access to an oracle that can tell me the future. Our insight, which we learned from belatedly, is that we should use an object's aggregate delay, or its true latency cost. Since I didn't have time to go over belatedly's formulation, I'll give you the intuition instead. When we have a cache miss, it doesn't just affect the latency for that request, but it also affects the latency of subsequent requests that fall within Z time steps of the original miss. That is, the delayed hits. So we must incorporate their cost as well. Aggregate delay is precisely this. It's the cost of the miss plus the cost of delayed hits, which fall within Z time steps of the miss. And this depends on the characteristic burstiness of objects. Here's an example of how to compute the aggregate delay. We have a Z value of 5 and 3 requests to A, the original miss plus 2 delayed hits. So in computing the aggregate delay for A, we would count the miss as well as the delayed hits, but ignore the request to unrelated objects B and C. This yields an aggregate delay of 8. So does this metric work? Well, almost, but not quite by itself. Consider this example, where we have a cache of size 1 and our Z parameter is 3. We need to decide between these two objects, A and B. A has an aggregate delay of 6 and is used 100 time steps in the future, while B has an aggregate delay of 5 and is used just 10 time steps in the future. So which of these should we cache? Well, every time step that we choose to cache A saves us 6 over 100 units of delay. On the other hand, every time step that we choose to cache B saves us 5 over 10 units of delay. So it seems like caching B is a better idea, despite the fact that A has higher aggregate delay. This tells us that our online algorithm should not only account for aggregate delay, but also the time until this object is reused again. Combining these observations, we have our heuristic. The algorithm itself is simple. In making an eviction decision, we compute the rank of an object, which I'll describe shortly, and we evict the object with the lowest rank, where the rank is defined as the ratio of aggregate delay to the time to the next access for this object. There's just one final snag. Both aggregate delay and the time to next access rely on future information, which we don't have access to in the online setting. Fortunately, as a standard in caching literature, we can use the past to make predictions of the future. Let's see what this looks like. We first consider the denominator, the time to next access. Recall that Belody chooses to evict objects that are used farthest in the future, which means that it ranks objects by 1 over the time to next access. We also know that Belody is hit rate optimal in the absence of delayed hits, which means that almost all hit rate optimizing algorithms aim to operate as close to Belody as possible, and the ranking function is an approximation of 1 over the time to next access. As a result, we can use these existing caching algorithms, such as LRU, LHD, LRB, or GD-wheel, to name a few, as estimators of the denominator. So now that we have the denominator, let's look at how to compute the numerator, or an object's aggregate delay. To do this, we pretend that every past request to the object resulted in a cache miss, incurring some delay cost. Then, we use the average of these delay costs over an object's entire lifetime as an estimate of its future aggregate delay. Here's an example. Let's say we have z equals 3, and we see 2 consecutive requests to object A. At time t1, we would compute object A's average aggregate delay as 5. Later, we have 3 consecutive requests to A. At time t2, we would update our estimate of A's aggregate delay as the average of the latency costs seen so far, yielding 11 over 2. If both requests to A appears immediately afterwards, we would once again update our aggregate delay estimate at time t3. We call this estimator the average aggregate delay. And while it's simple, we find that it serves as a good heuristic for an object's true aggregate delay, with a Pearson correlation coefficient of 0.7 between the two. Putting these estimators together, we're now ready to compute the rank of each object in a real cache. In order to evaluate our online caching algorithm, we return to our key value store implementation. We deployed our caching node in a local server cluster at CMU in Pittsburgh and set up virtual machines in 3 different locations around the world. One in Los Angeles, one in the Netherlands, and one in Singapore. Using the setup, we measured the average latency provided by LRU and its MAD variant for each origin location. As the RTT increased from 68 to 223 milliseconds, we saw latency improvements of 12 to 18%, going from origin A to origin C. Observe that as Z increases, so does the improvement provided by the MAD variant. Here's an interesting question. What happens when multiple non-uniform backing store latencies are involved? That is, different objects experience different miss latencies. To answer this, we distributed our objects uniformly among the 3 origins and reran our experiments. The bars labeled multi-backend represent this scenario. Despite the fact that this differs significantly from our theoretical formulation, MAD generalizes to this scenario as well, yielding a latency improvement of 17% over LRU. We repeated our experiments in simulation, this time testing a variety of application scenarios, z-values, and baseline algorithms, and we saw similar improvements across the board. Unfortunately, I don't have time to go over these results, but if you're interested, we present all of these graphs in the paper. So in conclusion, we see that cache requests result in not just hits and misses, but also in delayed hits. In order to truly minimize latency, high-performance caches need to consider the impact of delayed hits as well, especially as we look forward to ever-increasing trends in bandwidth. If you have any questions about this work, please feel free to reach out to me, and the code for both the simulator and belatedly can be found at this GitHub repo. Thank you.